Hello, welcome to another episode together. Today we'll be talking about impulse and momentum. Before we continue on, it's always nice to know about a bit of history about how everything came to be. So let's rewind back in time to the world of Galileo Galilei, all right, the father of physics. He was the guy who decided to drop things from the Tower of Pisa and noticed that uniform acceleration does exist. And that's why the kinematic equations are often named in honor of him. Sometimes they're known as Galilean equations. Fast forward a century into the future, and we talk about the story of Isaac Newton, how an apple fell on his head one day, and he discovered this notion of gravity, as well as this very famous formula, F net is equal to ma. He did discover other things. However, the reason why I want to show you this timeline is that, we know that, like many other people, we die, and you don't really know what happens in the future. All right. Now, yeah, he did exist during the same timeline as Robert Hooke, and if you've heard of stories, they hated each other. In fact, there's one story where Isaac, he apparently took Robert Hooke's pictures and burned them so that no one would know what he looks like. Anywho, the reason why I'm showing you this is that Newton, he had no idea about the notion of what power was, what energy was, and even crazier, he didn't even know what a periodic table was, or even the parts of an atom. All right. None of that existed back in his time. So, that's kind of weird to think of. He was able to talk about forces that cause objects to move, yet not know about something as simple as kinetic energy and potential energy. So, he had his own ways of describing things, because after all, he probably saw, objects rolling on the front of his desk, and he had some sort of way of describing, it and its motion and whatever that contains to make it move. And back in his time, he didn't call it kinetic energy. Instead, he called it momentum. And that's what we'll be focusing on in today's episode. P equals mv. Alright, so what exactly is momentum? Well, momentum by definition, it's a vector quantity of motion of a moving body. Why vector? Well, if you take a look at the formula, you'll notice that momentum is equal to mass times velocity. Anytime you multiply a scalar by a vector, you end up with an answer that is a vector. So momentum is a vector measurement. And that's the unit that he used back in his day. If you multiply mass by velocity, the units will be in kilograms times meters per second. And yeah, it would be nice if there was a new unit named in honor of him so that we don't have to say the units of momentum is kilograms times meters per second, but we don't have anyone in that honor yet. So we unfortunately have to stick with that crazy long unit. Now, similar to momentum is this terminology called impulse, which, by mathematical definition, it's the area underneath a force-time graph. There's a formula for it, where impulse is equal to force times time. Force is measured in newtons, and time is measured in seconds. So, how did these two universes link together? Well, momentum is the quantity of an object while it's in motion, but you can easily cause the object to either speed up by applying a force to it or cause it to slow down. And you're going to apply that force over a duration of time, meaning that you're going to apply something known as an impulse. So that's what an impulse is. It's a force applied onto an object over a duration of time to cause an object to have a greater or lesser momentum. So by mathematical definition, impulse is equal to the change in momentum. So momentum final subtract momentum initial. Here's a cleaned up version of it. Okay, impulse is equal to momentum final, subtract momentum initial. And let's just do a bit of brief derivation to create other equations now, all right, based upon what we've learned so far. So we know that if that momentum is equal to mass times velocity, then yeah, we can stretch it out to this bigger formula here. We're talking about the same exact object, so this mass here and both of these, they're exactly the same. So we could just factor it out. And if we recall in kinematics, V2 minus V1, well, that can be simplified down to a delta. So that's equal to m times delta V. In other words, impulse, by definition, is equal to mass times delta velocity. All right, so I'll give you that formula here. So you can either read it like this, you can read it like that, or you can read it like that. Up to you. All right, cleans it up because it expresses a whole lot of ideas all at once. Next, let's talk about the impulse momentum theorem, which simply states this, that there's a cause and effect for every given object, right? where the impulse will result in a change in momentum. An impulse will result in a change in momentum. All right. And yeah, this may seem like a brand new formula to this, but trust me, you've seen this formula before. Ready to be mind blown? All right, let's take this formula over here, and now let's divide both sides by delta t. And if you recall back in kinematics, the definition of acceleration is what? That's right, the change in velocity over the change in time. So we can replace this v delta t by acceleration and effectively get F net is equal to ma. So we have seen this formula before, just not rearranged in this fancy format. I swear I had another PowerPoint slide. Is it hidden? Yeah. Why are we studying this stuff here? Okay, why momentum versus force or even energy? Well, for one thing, energy was discovered, almost a century and a half after Newton died. All right, and there are specific differences between all of these. One problem about measuring force is that that force is equal to mass times acceleration. It doesn't have any notion of how fast you're going. All right, so your F net will never tell you how quickly you're moving, because if your F net's equal to 0, well, you could either be stationary, moving rather slowly, or moving insanely fast. You wouldn't know, all right, because F net, if it's equal to 0, then your acceleration is equal to 0. Your velocity just remains constant, and that's it. All right. So that's the advantage. Momentum, well, it's calculated using velocity. So the greater your velocity, the greater your momentum. And the lower your velocity, the lower your momentum. And if your velocity is at 0, then your momentum is at 0. F net can't factor in velocity. So this is how we deal with velocity. Now, momentum is different than energy or kinetic energy, because kinetic energy is calculated using speed. And this is another thing I want to point out as well. Speed, you'll see that there's no arrow on top, so speed is a scalar quantity, and momentum, as we discussed earlier, is a vector quantity. So momentum, we can determine direction after collisions or whatnot, but with regards to energy, well, there's no direction in our final answer. We'll never be able to figure that out. So when would you use one over the other? It depends on what numbers you're trying to get, and that's the one that you would choose to use. All right. So there are advantages and disadvantages of these two different types of calculations. As of now, we're just going to focus on momentum strictly, and then later on we'll fast forward 100 years in time and make these two fall in love. All right, but we'll save that for a future episode. Other things to keep in mind. If you recall in kinematics, the area underneath a VT graph tells you what? That's right, it tells you displacement. So you have an area of the shape of that of a rectangle. Well, areas of a rectangle is pretty much base times height. And that's what we have here, a height times base. We can also define the same thing over here as well. I did mention earlier that impulse by definition is the area underneath a force time graph. So if your force remains constant all the way through, then yeah, the area you create is a nice pretty looking rectangle. So the formula should just be J is equal to F times delta t. In calculus, the area underneath the curve is called the integral. So I hope you can appreciate the title for these two graphs here. Okay, that displacement is the integral of a VT graph. Meanwhile, impulse is the integral of a force time graph, or the area underneath it. Now, these graphs over here, they're rather pretty, right? We have lovely looking rectangles. But in life, we don't get lovely rectangles. For example, when a bat makes contact with a ball, yes, the force that's applied to the ball suddenly spikes up to a very high value. But as the bat continues to swing, well, then the ball starts to leave the bat. For one thing, the mass of the ball is much less than the bat. All right, so it starts to move away, and the force applied to the ball quickly diminishes. Now, yes, this does look, roughly like a triangle, so you could approximate it to a triangle and calculate it out. Or in this artist's rendition, what they did was they just took this piece over here, shoved it in there, took that piece there, and hoped for the best over there, and they tried to average it out to an approximate rectangle. All right. But, that's all approximations. If, in theory, you can measure your starting point of your force and the end point of your force, then you've effectively made a measurable triangle. And as you can guess, if you can find out the area of the triangle, well, now you've determined the amount of impulse that's done there. So yeah, you probably want to do half base times height for that. All right, but let's just show you another generic equation. All right. Let's say that the force uniformly either increases or uniformly decreases. All right. But before we get to the answer over here, let's talk about the area underneath the VT graph one more time. As mentioned, the area underneath the VT graph tells you displacement. Now you could split this up into two separate areas and calculate it out, or if you recall the area of a trapezoid, well, the surface area of a trapezoid is equal to half times height 1 plus height number 2, so height 1 would be here and height 2 would be on the far end, times the base. In fact, if you recycle that into kinematics, that's why it looks like that. In fact, we can also recycle this one more time with regards to the area underneath the force time graph, which would give us a very similar formula. Something to point out, if the background shaded out in light blue, this is a formula that will be provided for you in any sort of future quiz, test, or exam. All right, so that's why I'm trying to show you this formula here. So if you have any questions in your homework that tell you that the force started off at a certain value and uniformly increased up to a final value over duration of time, now you can calculate out how much impulse was applied onto the object. The law of conservation of linear momentum states that in any sort of collision, momentum is conserved. In fact, this is 100% true. All right. Energy may not be conserved. For example, if you throw, a dart onto a dartboard, it gets stuck and then the kinetic energy disappears. All right. However, the momentum is conserved. In fact, when you throw the dart onto the dartboard, technically speaking, when they hit each other, they start moving to the right, and if this is connected to the Earth will also move to the right as well. Will you notice it? Probably not, because the mass of the dart is really small, meanwhile the mass of the Earth is rather large. All right. So even though an impulse has been applied, by the time the dart has hit the dartboard, we won't notice it as human beings because the Earth is so huge. Meanwhile, if this dartboard was on skates, you can imagine the whole system connected together, they'll start moving. Not very quickly, but they will move. Right? So momentum is always conserved 100% of the time. Okay, so total momentum of a system before a collision is equal to the total momentum of a system after a collision. Maybe you've seen this toy before. In fact, do you see the Easter egg? Pretty cute, isn't it? Okay, back to this definition over here. Let's make a formula for this. All right. We know that momentum can be described either by the letter P or by the letter rho, and I'll stick with the letter rho because sometimes P is used for other measurements like power. All right, so we'll stick with rho. All right, so total momentum, rho total initial, is equal to rho total final. Yes, we have an arrow on top because momentum is a vector quantity. Of course, trying to write this out takes a long time, so sometimes we like to use shortcuts. If you're familiar with calculus, you have the function y is equal to something, something, something. Well, the derivative, they'll just use an apostrophe. All right, and if you want to do the second derivative, you'll put two apostrophes. Here's where the world of math kind of messes around with the world of physics, or vice versa, depending on which one you learn first. We also use a apostrophe or a prime in physics as well, and sometimes that's used to describe the final end result. That way, this ugly looking thing over here can be written down as something as clean as just this. Total momentum at the beginning is equal to total momentum at the end. Okay, and we'll use this notation for the remainder of this unit because if we don't, it'll just take forever to write out everything like this. And you'll see what I mean when we get through our examples. Like this one, okay? We have a gentleman who's standing on top of a skateboard, and this gentleman is also holding on to a ball. This gentleman throws the ball in one direction. What happens to the gentleman? I think from experience, if you've ever done something like this before, you'll notice you move in the opposite direction. In fact, this is the principle of rocket science. All right, so this gentleman here was a rocket ship. There you go, there's a lovely rocket ship. He needs to throw something and eject something out of his thrusters in order for the ship to travel in the opposite direction. All right, so let's go and do this math right now and talk about the implications of it all. So we'll start off with our givens. To make our lives easier, yes, momentum is a vector quantity, but we probably want to treat everything as a scalar first. It just saves a lot in our penmanship. All right, so we'll take it that forwards is positive, and we're going to take everything from the reference of Harold. So Harold is a mass of 50 kilograms. Harold is stationary. The ball is stationary relative to Harold. the ball has a mass of 10 kilograms. Afterwards, the ball is moving at 10 meters per second positive, which is towards the forwards direction, like so. Okay, and here are our givens, and you can see why we want to use the apostrophe. It just keeps things nice and clean. We also stated that the momentum before any sort of collision, in this case over here it's an explosion, is equal to the momentum after. Okay, so total momentum before is equal to total momentum after. In the story over here, the momentum is based upon the momentum of two objects, the momentum of Harold and the momentum of the ball. So the momentum of Harold and the momentum of the ball before they separated should still be equal to the momentum of Harold and the momentum of the ball afterwards when they separate, because momentum's always conserved. Here it is all typed up nice and clean. Okay, well, let's go through one thing. This is one of those examples where you have an explosion. So the energy comes from internally, but the momentum is conserved. All right. You'll notice that the initial momentum is at 0. VH is equal to 0 and VB is equal to 0. So all these terms over here go to 0. What this tells us is that afterwards, the total momentum of the system also has to net to a value of 0. And yeah, the units are in kilograms times meters per second. Now remember, we're treating everything here as a scalar quantity, so we may see some sign changes when we work through the math here now. Alright, so let's focus on this guy over here, and we're trying to find out the speed of Harry now, or more specifically the velocity of Harry. So VH apostrophe is going to be equal to, when we bring this term over to the right hand side, we're going to have negative m subscript b v b apostrophe all divided by the mass of Harry. I think I have that all animated out. There you go. Okay. We then sub in all our values, so negative mass of the ball, velocity of the ball afterwards, which is at positive 10 meters per second, and the mass of Harry, which is at 50 kilograms. Go through all the calculations and show your work, and you'll get an answer of negative 2 meters per second. Remember our thought experiment? If Harry throws the ball towards the right, we know that Harry at the end will end up moving towards the left on top of his skateboard. This actually abides by Newton's third law. For every action, there's an equal and opposite reaction. All right? So that's why Harry will move at a speed or a velocity of negative 2 meters per second, where if positive is forwards, then negative must imply backwards. Remember that if this is a vector-based problem, always keep your final answer as a positive statement. Let's do another example. Oh, actually, before the next example, I just want to talk about one more thing, okay? With regards to rocket science, well, you can see the consequence of what's happening here, right? We have a ball, which is much less in mass than the larger object. So you can imagine in a space rocket, if they're trying to eject something, which often is water vapor particles, well, the particles are really tiny. So when you throw them in the opposite direction, the ship won't move very quickly at all. You're not going to get to your destination of the moon or wherever else you decide to go. So how do you compensate for that? Well, you'll notice here that the only factor that you can adjust if you cannot adjust the mass of the two objects is that you can adjust the speed. And that's why thrusters are built the way they are. They actually eject the speed of the water droplets at insanely fast speeds. That way you're able to do the action-reaction pair and be able to move in the opposite direction, at least at a decent speed. Alright, the next example is that of an inelastic collision. That's one where two objects are moving freely and then they stick to each other, like the story over here. Alright, here's Jacob. Alright, Jacob's walking and having a good time, walking at 1 meter per second forwards. Irene, on the other hand, where Irene with half the mass wants to say, hey big brother, I want to say hi to you. So she's running in the opposite direction, and then once they click together, they end up moving backwards at 2.0 meters per second. Alright, so she's going to run towards them, they're going to hug, get stuck to each other, and move backwards. Okay, and the question is, how fast was Irene traveling to make this happen? And you can imagine that she probably had to move very quickly, especially with her tiny little mass. Okay, so as with all word problems, let's start off with our givens. What do we know? All right, so we know that the speed of and we're going to assume that positive is forwards. All right, so the velocity of Jacob, which we're going to treat as speed for now, is traveling at positive 1.0 meters per second. No, you don't have to put in the plus sign. We're just emphasizing it here. That's all. All right, and after Irene tackles him, them together, so I'll just call it V apostrophe, which is equal to V I apostrophe, which is also equal to VJ apostrophe. All right, that's why I just want to keep it nice and clean. V apostrophe is at negative 2.0 meters per second. What else do we know? Well, we know that the mass of Irene, she's only half the mass of Jacob. So in other words, the mass of Jacob is equal to double of the mass of Irene. I know it's very tempting to assume that Irene has a mass of, let's say, 1 kilogram and Jacob has a mass of 2 kilograms, but what if those assumptions affect our final answer? What if the initial masses that you chose randomly affect the destiny of the calculations? You never want to do that. Instead, you want to create an equation. And when you create the equation, if the letters of I and J remain at the end, that means the initial mass does matter, and you won't have a final absolute answer. You'll just have an expression, and that's it. All right. Meanwhile, if the masses disappear, then it doesn't matter. As long as Irene is definitely half the mass of Jacob, you're definitely going to get these results each and every single time. Okay, so that's why we want to treat it as a mathematical expression and hope that the units will divide themselves out. Now we're trying to figure out what the velocity of Irene was. That's what we're trying to look for. So VI as a question mark. Okay, I'll need some space here, so unfortunately I need to erase my cute little picture. Okay, so as stated, total momentum of any given system before the collision is always going to be equal to the same value afterwards. It doesn't matter if it's the example of the first one, which is an explosion, where the total momentum was at 0 and ended up being at 0 at the end, or if there's a measurable value at the beginning, you're going to have a net value at the end, or total value at the end, that's going to be the same, right? And that's always true. Momentum is always conserved in all circumstances, even if it's in these weird ones where they stick together. Also known as a completely inelastic collision, but we'll save that for tomorrow's adventure. Okay, so let's expand this out. Total momentum is equal to the momentum of Irene plus the momentum of Jacob. All right, so momentum of Irene plus the momentum of Jacob is equal to the momentum of Irene after the collision plus the momentum of Jacob after the collision. Rho is equal to mv. In fact, you probably could have skipped out the one above, but I'll just formally write out everything here. All right, so there you go. I, J, J, I, J, J, apostrophes there. Done. Keeps the notation relatively clean. All right, so again, VI apostrophe is equal to VJ apostrophe. We mentioned that earlier. All right, so we could just factor that out. So V apostrophe MI plus MJ is equal to what you see on the left. I'll just stick with that. Oh, yeah, that looks cleaner. INJ. We also stated that MJ is equal to 2MI, so let's just sub that in and see what happens. All right, so MI, VI plus MJ will be replaced with 2MI. VI is equal to V apostrophe MI plus 2MI. MI plus 2MI gives you 3MI, so 3MI. I'll just stick with the clean I, times V apostrophe is equal to what you have on the left. J. Whoopsie daisy, almost made a mistake there. J. All right, and what you'll notice here is that all these terms here have an MI. In other words, they're going to divide each other out. So really, the initial mass of Irene didn't really matter. As long as Jacob's definitely exactly double of Irene, the outcome will be the same each and every single time. Again, I want you to solve these problems this way. Don't assume any numbers. All right? Assumptions may lead to disasters. So this leaves us with VI plus 2VJ is equal to 3V apostrophe. And since we're trying to figure out how fast Irene was traveling, that's equal to 3V apostrophe minus 2VJ. So let's sub that in. 3 times negative 2.0 meters per second minus 2 times 1.0 meters per second. 3 times 2 is 6. That's a negative 6. Negative 6 subtract 2 will give you negative 8 meters per second. Again, don't leave your answer as a negative if it's a vector. If you know forwards is positive, then therefore the velocity of Irene, she was traveling at 8.0 meters per second backwards relative to Jacob before they collided. And that's our answer. Here's the typed up answer key, and it gets to the same answer as well. Oh, one more cool thing before we end off. There's a really cool demo here. You can look it up online afterwards, or even just try it out yourself. What you need is a very big ball, all right, heavy. So not a beach ball, but something like, I don't know, a basketball, let's say. All right, so you get a really huge basketball, and then you're going to put a tiny little ping pong ball on top. And what you're going to do is you're going to take this whole crazy apparatus, hold them very carefully, and let go of them and let them hit the ground. And the question is, the moment it hits the ground, what happens afterwards? Do they stay together as a system and bounce all back up together? Or how about you guys try that experiment and see what happens, all right? And try to explain it. Why does that bizarre outcome happen? All right? Why did the ping pong ball do the crazy thing that it did? And you'll only know what it did if you try the experiment yourself out. So try it out, get through the homework, and we'll discuss more about this in tomorrow's episode.